these last two problems are a lot more like you would see with word problems. And the first one says if home plate is 60 feet from the pitcher's mound, how many seconds does it take a 90-mile-an-hour fastball to reach home plate? If you analyze what they're asking for, here is the question: how many seconds? So you know that you want your final answer to be in seconds. This also tells you that your initial information will have only one unit. So when you see this 90 miles per hour, you know that that is not a starting point because it has 2 units in it. This is going to be a conversion factor. In fact, this is the factor, which is speed, that is going to allow you to convert distance to time. So our starting point is the 60 feet. So when we start with those 60 feet, we need to get them into seconds. And we notice that what is going to allow us to do that is the speed. But the speed is not in feet per second. The speed's in miles per hour. So if we can change our feet into miles, we can then use the speed to change it into hours. And this is the same thing as saying, I need to go to the beach. It's 250 miles to the beach. I'm going to average 50 miles an hour. How long is it going to take me to get there? It's the same sort of problem. But we don't want our time in hours. The batter is not going to wait hours for the pitch to come to him. We want to convert those hours down to seconds, and we'll use 2 steps to do that. We'll convert it to minutes, and then we'll convert it to seconds. The qualities that you need, we've already done the feet per mile. You should know that there are 5280 feet and equal to 1 mile. And the 90 miles per hour will be the conversion we use that will change distance into time. And then you should know there are 60 minutes in an hour and 60 seconds in a minute. So when you start off with that 60 feet, the first thing you want to get rid of is feet and change it into miles. And here's where the 5280 comes in. And now we want to get rid of the miles, and this is going to allow us to change it into hours. And our pitch is going 90 miles for every hour. We now need to get rid of hours and change them into minutes, and there are 60 minutes in 1 hour. And then the minutes will get converted into seconds, and there are 60 seconds in 1 minute. So mathematically, you're going to have 60 times 60 times 60 divided by 5280, push equals, and then divided by 90. So doing that on the calculator, get that over here, 60 times 60 times 60 divided by 5280 equals divided by 90 equals, and this is 0.45, and that probably is an appropriate way to round that. I hope 0.45 seconds. This means the batter has less than a half a second to hit the ball. Now, the next conversion examples are ones that more relate to chemistry and to health sciences. Suppose you have a 180-pound patient. The drug dosage is 5 milligrams of drug per kilogram of body weight. So this does not mean that 5 milligrams equals a kilogram, but you're going to give 5 milligrams of drug for every kilogram of body weight. And this is where the term weight is used incorrectly. And the drug concentration is 0.55 grams per cc. You want to know how many cc's to inject. Well, when you look at this, you want to know how many cc's. That has 1 unit in it. So I'm going to look for the piece of information here that has 1 unit, not for the other pieces, which are conversion factors. So I'm going to start with my 180-pound patient. Since my drug dosage is in kilograms, I want to get his weight or mass in kilograms, and there's 2.2 pounds in 1 kilogram. Once I have the information in kilograms, I can take those kilograms of body weight and convert them into milligrams of drug. And there are 5 milligrams of drug for every kilogram of body weight. And now, for every cc, there are 0.55 grams. Well, I can't put 0.55 grams with that milligram, but this would be 550 milligrams by moving the decimal point 3 places to the right. If you remember your metric conversions, this is the unity. You're going to move 3 places to the right to get to milli. So I'll have 550 milligrams per cc. Now, I want you to note that I put in some colors here. Everything that is in red represents body weight, and everything that is in blue represents the drug. So when I do this problem, I'm going to have 180 times 5. I'll divide it by 2.2, push equals, and then I'll divide again by 550 and push equals. So bringing up my calculator, 180 times 5 divided by 2.2 equals divided by 550 equals. And that is equal to 0.74 cc's. And actually 0.7 cc's when you look at significant digits would probably be appropriate. This you could use like an insulin syringe, which might be a 1 milliliter syringe, and it should be lined off in at least tenths, maybe even hundredths. Now, you could also be asked this problem by giving the drug in tablet form, and you can reproduce the first part of this problem because the patient's body weight and the dosage did not change. But the way the drug is administered did, because we have 200 milligrams in a tablet. So we just have a slightly different setup here. So you have 180 times 5 divided by 2.2 equals, and then divided by 200. And doing that on the calculator, 180 times 5 divided by 2.2 equals divided by 200 equals. And this tells me that I'm going to give my patient about 2 tablets. Again, notice the units canceling out, and the only unit that's left is in tablets. This is what a set of conversion factors should look like, and this allows you to take the information that you're given. You know, these are conversion factors that are specific to the problem, and allows you to take your starting information and end up with the final information.